just so I can post this up for you guys, because I know this is a complicated subject. So sorry to everyone about forgetting the first bit of class. We just went over the very basic thing.
Where are we able to see the recordings?
I will put it up on my YouTube channel, and I will also post it up on Classroom when I get it up on the YouTube channel.
Alright, thank you.
Yeah.
I was
There-
wondering if you posted last week's too. Because
I did not, because I forgot to record last week's. I'm sorry.
Okay.
Yeah. I've been spacing recording them for a bit, but I will try to get back into the habit, because it is a good habit to get into, to have them all up for you. I'm sorry, guys. Okay. Other example with it's a little bit more complicated than this, and I just wanted to make sure everyone had this written down before I kept scrolling. Maybe I'll use a new color for the second one. We all good?
Wait, Mr. Scuderi.
Uh-huh.
Sorry.
No,
I
go ahead.
don't know if I missed something, but why are there like two different numbers that you're like there's the 12.011 and then there's the 1.008?
So that's the molar mass of, in this case, carbon, and this is the molar mass of, in this case, hydrogen. It's the molar mass that corresponds to that particular element that we're working with, right? Carbon goes here, hydrogen goes down there. Yeah, cool. All right. Let's do another example here that's a little bit more complicated. It doesn't work out as perfectly as this one does. And then we'll add a third step here, which will help us solve more problems. Let's see. Where was my example? There it is. So this other sample had 5.31 grams of chlorine and 8.40 grams of oxygen. I'll draw a little line to just separate these, even though it's separate colors, we know. Okay, so kind of the same steps as before, at least to start. Right, let's look at our little thing. We want to convert both of these masses to number of moles of chlorine and number of moles of oxygen. And then we'll do this formula and divide by the smallest number. So we need to look up, excuse me, 5.31 grams of chlorine. And we're going to divide by the molar mass of chlorine. I'm going to look it up on my P table. If you want to follow along with me, go for it. I'm looking it up, though it's the very first page of P table. It's the properties tab up on top. And it's that number that's on the bottom of the square, right? That's the atomic mass or the molar mass, kind of the same thing. 35.45 for chlorine grams per mole. Right, and this, this is a bit of a more compact notation here. It is the same thing as doing this dimensional analysis I showed you up here, but it's just a little bit quicker to write, right? And it's maybe easier to see what math we're doing too. 5.31 divided by 35.45 gets us 0.1, if I want to round, 1498 moles of chlorine. It's 149.7884344, and I'm going to keep that number in my calculator to do future calculations with. To get the number of moles of oxygen, I'll take the mass of oxygen here, 8.40 grams of oxygen, and I'll divide by its molar mass. And looking it up on my P table, it's 15.999 grams per mole. So this is going to be pretty close, a little bit under 2, or 1/2, I should say, sorry. 8.4 divided by 15.999. 0.525032846. I'm just going to write this. Moles of oxygen. So, that's this guy. Those are the masses. That's our first step. And we're going to do our little formula like we did up here for the carbon and hydrogen. So chlorine, Cl 0.1498, ... Oxygen, 0.5250, ... and we divide by the whichever one is smaller, so the 0.1498. I'm going to do, in my calculator here, I'm going to do this with that full precision number just to get something really close. I get, obviously, we end up with just a single chlorine, right? That 1.1498 divided by 0.1498 is going to give us 1. And for oxygen, we actually get, interestingly, 3.5505. I'm going to round it just to 3.5. There. So but the problem is, if I'm rounding to 3.5, still a problem because this is not a whole number still, right? So the next step I want to take in order to get these into an actual nice whole number formula is I want to convert this number. If I still have a decimal, I'm going to convert it into a fraction. So 3.5 converts in pretty nicely into 7 halves, right? I'm hoping that that's like converting decimals to fractions is something you guys have done a lot in math classes, right? I remember doing it a lot when I was in like pre-algebra and algebra kind of stuff. So I'm hoping that was something that your math teachers did for you a bit. And I'm going to scroll down a little bit so I have a bit more room to write. So yeah, I'm going to convert this to 7 halves. So what it looks like Cl, I'll put a 1 here. Usually you don't put the 1 in the formula, but I'll just put a 1 to remind myself there's only one of them. And O, 7 halves. In order to get this into a nice whole number formula, I'm going to multiply both of these subscripts by 2. I need to keep the ratio of them, right? Because this is the correct ratio. There's 1 chlorine for every 7 halves oxygen atoms. So I need to preserve that ratio. So everything I do to this one, I need to do to this one as well. So I'll multiply by 2, and it'll get rid of this denominator, right? Which will give me 2 chlorines and 7 oxygens. And that is my formula. And you can get more complicated with this, right? If I had, I don't know, I think this is a real, actual formula. This is a real molecule that can happen, or at least it's an empirical formula of one that can happen. But I'm going to go into the land of just totally making things up just to illustrate a point right here. So what if I had, instead of instead of this Cl1O7 halves, what if I had Cl1O7 halves, and then like maybe I'll have I don't know, an extra hydrogen 2/3. This is almost certainly not a molecule that would exist in real life. Right? I'm just making up these numbers to illustrate a point. But I have 2 fractions here. So it's not that much more work. I would do the same thing. I'd multiply by the 2 for all of these here to get rid of this denominator. And then I'd go through and multiply by the 3 to get rid of this denominator. So for the first one, it would go Cl2O7H, what would that be? 4/3, right? I multiplied all of the denominator, or these guys, by 2. And then to get rid of the 3, I'd multiply all of them by 3. So Cl, what would that be? 6. O, 7 times 3 is 21. And H, 4. And that would get me to my whole number thing, right? Doesn't matter what order I would do it in either. I could do the 3 first and then the 2. Either way. Okay.
Mr. Scuderi.
Uh-huh.
So up where you had the 3.5 after we divided the Cl or chlorine and oxygen.
Mm-hmm.
What if it was like 3.55? Would you still just round it? Like, what if you had 2 decimal points?
Right. So really, what this number really is 3.50. What does it end up being? 50516. So in that case, I did round it. Although it was much more clear. If it was more complicated than this, like if it was like 3.57, then in that case, that would be more difficult, right? Because it probably round to 3.6 or something like that. You could try converting this to a fraction. Yeah, I don't know. I think I'm gonna at least try for us in this class to make sure that when I assign problems, it's not going to end up with something like ambiguous like this. You know, it'll end up with like 3.33333, right? Like a third or 3.25 or something that's like easier to convert into a fraction, right? Like a nice quarter or a third or a half, something like that. I'm going to really try hard to make sure that that's the case. So, and I mean, basically when I write questions for you, I solve them myself to try to make sure that there's no things like this that pop up. I really try hard to make it so that it's not like really crazy difficult and ambiguous. Yeah, which is actually what takes me longest when I'm grading something is I try to solve the problem in the correct way or the way that I would do it, and then I try to solve it in multiple other ways that, you know, try to find where the mistakes could be. That takes longer than the actual like marking, giving you points for it. It takes forever. Yeah, so I'm going to try my hardest to just make it into something that rounds pretty obviously to a really easy fraction. Yeah. So I'll do my best. If it doesn't, then I made a mistake, or you made a mistake, or both of us made a mistake. If it doesn't, ask me about it, and I'll try to confirm. How about that? Let's see. What else is there? Oh, where are my notes? There we are. Yeah, well, I guess at this point, let me give you an example to try yourselves. How about that? You guys have seen a couple of these. You've seen two of them. So let me give you an example. This example actually comes straight from the textbook. It's hematite, which is an oxide of iron. It contains 34, your sample at least, contains 34.97 grams of iron, Fe, and 0.130 grams of, oh, no, that's the wrong question. 15.03, that's what it is. 15.03 grams of oxygen. And so it's asking what is at least the empirical formula, you know, the formula you can get to through these steps. So I'm going to give you 10 whole minutes to try to do this because it's your first time doing it. It might take you a while to get used to this process. So yeah, everyone try to do this, do your best. I'm going to give you the full 10 minutes. And when you have an answer, I don't care if it's right or not. I just want to see an answer. Give me a private chat and I will check it and I'll let you know. Okay. Let's go through this problem then, because I think a lot of people have gotten the right answer. A couple people have gotten close to the right answer. Let's try it. So again, those steps that we had up before, we convert these masses into moles of a substance. So iron, 34.97 grams of iron, divide by its number of grams per mole. I need to look up iron over here. I don't remember what the number is off the top of my head.
Why don't make it clean numbers? Why do we have to round?
Sometimes there are rounding errors for various things here and there. Sometimes, like, I'm sure if you had more precision on these two numbers, then we wouldn't have to round. But I think because they're rounding these two, then that introduces a little bit of imprecision. I think these two, it's because they've had to round these just to make it readable, right? You don't want to do 12 decimal places here. Let's see. Where was I was looking for the molar mass of iron. 55.845. There it is. 55.8 excuse me, 845 grams per mole. I need some water. I've been talking too much. Excuse me. I'm going to do this in my calculator. 34.97 divided by 55.845. So that's 0.626. 0.626197511. But moles of iron. And then for oxygen, 15.03 grams of oxygen. Its molar mass, I remember because we've done it before. 15.999 grams per mole. And this is the thing, like, I tend to, like, for some reason, when I do one of these a lot, like, we've done oxygen a lot, I just tend to remember that number. It just sticks in my head for no good reason. I think it's the best way to memorize things, just by using them a ton. 0.939. So we're going to divide by the 0.626 for both of them. And I get really damn close. So it'd be FeO 1.5. And the number here is actually 1.50021. It's so close to 1.5. I don't feel bad about rounding to 1.5 at all. So yeah, 1.5. So we're going to use our trick of converting 1.5 into a fraction. Halves. Halves makes sense, 1 over 2. So it's going to be what? 3 halves, right? So that means we want to multiply everything by 2. So that would give us Fe2O3. Elena, there you go. I just saw yours there in the chat.
How do you know that's not Fe3O2?
Well, so I had this formula, right? When I converted to fraction, I had Fe, there's a 1, and an O 3 halves, right? If I multiply everything by 2, I'm not going to get an Fe3, I'm going to get an Fe2. 1 times 2 is 2. And then I can have a 3 over here.
Why do we know it's FeO 1.5?
So I did this division here. I had the 0.626 moles of iron and the 0.939 moles of oxygen. When you divide by the smallest one, that's what you get. You get a 1 and a 1.5. Yeah?
Right? I understand.
So you can't get anything else. If you divide by the smallest one, you must get a 1 for the iron because it's dividing by itself. You have to get a 1. You can't get anything else.
Oh, okay.
Right?
That makes sense.
Yeah. No worries. No worries. And then there's at least our empirical formula. And Fe2O3 is actually a real thing. It is the most common oxide of iron. And in fact, I was just looking it up on P-Table. If you want to look it up on P-Table yourself, you can go to Compounds tab on the top and put in Fe and O. Fe2O3 is right there. If you can click on it, iron 3 oxide. So it is an ionic compound. It's iron 3 plus. Technically, it's 3 plus ion and the O2 minus ion. Whoops. So yeah, this would be iron 3 oxide. Would be its name. And yeah, I was just looking it up. It is apparently the most common form of the main source of iron for the steel industry, is what Wikipedia says. That's pretty cool. It's called hematite, sometimes called rust, although rust is a little bit different in actual fact. Oh, that's cool. I don't know. That's neat. So we found we have a sample of rust, basically, of hematite, I suppose. Let's see. Oh, yeah, and the thing is, I have a ton more examples. I have like 6 examples I can give you to work through. which will be useful. I think I'm going to save them for next class, though, because right now what I'd like to do is I'd like to move on to the last step. So we can get to this empirical formula, right? We're calling these empirical formulas because they could be any number of these things. Excuse me. But there is a way to get to the actual formula. The actual formula. And in fact, I think for this first one we did CH2. I think the actual formula is C2H4, is this one. If I'm just looking at the compound here. Oh, maybe it's CH2. Ethylene. Interesting. I don't know. It could be both. But you need one more piece of information in order to get that. So I'm going to start, if everyone's okay with it, I'm going to start a new page here real quick. So yeah, we only have like 10 minutes left, so let's get to this. Say we have some sample, right? We have CH2, like that. And we don't know, this is an empirical formula. We don't know if this is the actual formula. It could be C2H4, it could be C6, or C3H6, sorry. It could be any number of things. To get to the actual, what's called molecular formula from the empirical formula, you need to have the actual molecular mass of whatever substance you've got, which is another thing you can get from various lab instruments. You can actually find the mass of a molecule or the mass of a mole of this stuff. Let's first, maybe this is a good chance to answer Lola's question, the difference between calculating the mass of a covalent compound versus an ionic compound, like why they're considered different. So let's calculate the mass of this compound, right? We do our little table like we had last time. I think I remember all the numbers here. Mass in AMU. Carbon was 12.011 AMU. Hydrogen was 1.008. Number of them is 1 carbon, 2 hydrogens. And then total AMUs 12.011, and then was it 2.016 would be, I think. And so that would get us 14 point, what is this? 027, I think, AMU for the total formula mass for this guy. So no matter if it's a covalent or ionic compound, this is the same process we use to get to the mass, right? But if it's a covalent compound, we call this the molecular mass. Or in this case, I suppose it's a formula mass, because we don't really know the formula yet. And if it's an ionic compound, we call it a formula mass. And that's because for a covalent compound, as long as we know that this is the exact formula that it is, right? For a covalent compound, that is the molecule. See, it's just a carbon and 2 hydrogens. And I could even do the Lewis diagram for it. Carbon has 4 valence, hydrogen has 1. So it'd be 6, 5, 6. So that wouldn't be... Yeah, that's not a great... that molecule doesn't really work for the Lewis structure. It doesn't fill the octets. But for the covalent compound, the reason we call it the molecular mass is that we know for a covalent compound, this is the whole molecule. It just exists by itself. Whereas for an ionic compound, like salt, NaCl, we'd call it a formula mass, because ionic compounds can sort of crystallize together, right? They like for salt, it's a sodium and a chlorine. I'm going to draw a sodium as a filled-in circle and a chlorine as an open circle, right? But the way that ionic compounds work is you can actually bond to other versions of yourself, right? You could have another NaCl molecule over here, and you make a molecule out of this. And in fact, this is what happens for salt. It makes nice cubes like this. And so it's not exactly like the one sodium and the one chlorine aren't the whole molecule. It could be many of them. And in fact, you don't really know how many of them it could be. You could build this brick molecule up to quite large indeed. So the mass of the molecule might be many times what that formula mass is. That's the only real difference. It is, for our purposes, for doing this math, it is a pointless distinction because the calculation is still going to remain the same. Yeah. In the 5 minutes we have remaining, let me introduce how to use this formula, this mass we just got here, empirical formula mass, along with the actual molecular mass to get to a real formula or a real molecule. So having looked this up, I do think, this is pretty likely. So let's say your machine told you, we did this problem, right? We figured out the empirical formula at least was CH2, right? And your machine also told you some extra information. It also told you that the molecular mass of this guy is maybe 28.054 grams per mole of the whole molecule, right? So this is the extra bit of information, is the number of grams per mole of the entire molecule. And you'll notice that is actually different from the mass, the molecular mass we calculated over here, right, for this formula. So that's telling us that this empirical formula might not be entirely correct. To get to the real molecule formula from this empirical formula, we're going to need both of these numbers. I'm going to highlight them in red because it's important. This molecular mass, the actual molecular mass of the actual molecules, and this calculated mass from the empirical formula. We're going to need both of these, right? To get to the real formula of this, we're going to take this molecular mass, the actual molecular mass, 0.054 grams per mole. And we're going to divide by what we calculated is the mass of our empirical formula, the 14.027 grams per mole. Right, and I'm switching between AMU and grams per mole here. The 14.027 AMU was the mass of a single molecule of CH2, theoretically. And the 14.027 grams per mole is the number of grams of a mole of that substance. I hope that's not too crazy. If we do this division, we get, well, just because I worked it out exactly, it's exactly 2. Which is telling us that we need to do, if we have our formula CH2, we need to multiply all the numbers by 2, basically. Which would be a C2H4, right? It's a 1 there for that C. Usually we leave the 1 off. So multiply by 2, and that gets us to the actual molecular formula. That's all. One way to do it is I don't know. what would I call it? If I have element X and element Y, and I found out that this number here was C, I guess, the actual formula would be like that. Does that make some sense? How did I get 28.054? Well, what I did is I just multiplied this by 2. But in reality, how would you get it in a problem, is what you're asking? You'd be given it. It would be a given number. You wouldn't have to calculate that. It would just be something that you're given, right? It'd be something that's in, like, you know, your problem would say, and actually a common way to phrase a problem like this would be like, there's, I don't know, I'm going to make up some numbers, 3.68 grams of hydrogen, 44.39 grams of carbon, and 27.222 grams of oxygen, right? Like, that's how we would phrase those previous questions we were doing. And I would also give you the fact that the whole molecule, the entire molecule, had a molecular mass of, say, 137.68 grams per mole for the entire molecule, right? That'd be the extra bit of information that you were given. It's exactly the same as this. You just have to be given it. There's no other way to calculate it. And so from this information, almost certainly, because I literally just made these numbers up, it would not work out well. But you could imagine a problem like this. This would be able, with this information, right? The masses of each element involved and the total molar mass of the molecule itself, you can actually figure out the real formula of the molecule, which I think is super cool. Next class, all we're going to do next class is just a ton of examples of this. And maybe there's actually one more tiny thing we can do in terms of testing things out. So we'll do that next time. And I think I'm going to do my best. I don't know. I'll cross my fingers. If I have time to do it, I'm gonna have a short homework for you guys to do. Assign it at the end of next class. Due next week, probably. So that's what to look forward to. And that being said, we are past time for the end of class. So I would say go have a nice lunch.
Thank you, Mr. Skinner.
Yeah, guys.
Thank you.
Okay, I'm gonna stop my recording here.